Welcome back to the 21st chapter of CCE2. As we have mentioned earlier, in this second video we will learn more about the fundamentals, functions and main services of operating systems.
Last time we learned about the scheduler, and we've said that this is the basis of all OS. However, the scheduler alone is not enough because threads need to be created, started, and stopped. They also need to communicate with each other and with the outside world, synchronize data access between them, and they have to access shared resources. The combination of these tasks is usually called an operating system. Let us first look at the most important component of the OS, the scheduler. The first question is, when and why do we stop a thread from running? There are several strategies for this. The simplest solution is called cooperative multitasking. In this case, the programs themselves ask the scheduler to interrupt them. This may sound strange, but it has its advantages. In a program, there is often a wait cycle or a need to do something that consumes resources for a long time. At such points, the cooperative program periodically calls the yield function. This starts the OS scheduler, which stores the context of the currently running thread and starts another one. Then, the other thread will also call yield, and sooner or later, the control will return to the original thread. We can see that if the thread does not call yield, no context switch occurs, so the thread must cooperate. However, the interrupt here is not random, and this is very important. There is no need to worry about concurrent data access, for example, another thread modifying memory while we are using it, so synchronization is very simple here. So, in the cooperative multitasking case, the task change always happens at a known point.
Cooperative multitasking also has a disadvantage, which is the response time. We cannot predict when a thread will run, and it is also possible that a badly written program might not yield control for a long time. This can be addressed by forcibly preempting threads. This can be done at fixed time intervals. Thanks to this, each thread can run for a maximum of one time slice, solving the problem of non-cooperative threads. However, a thread can now be interrupted at any time, so we need carefully written synchronization solutions. Time slice-based task switching, as good as it sounds, isn't perfect. The response time will not improve significantly, but we will introduce many unnecessary context switches and synchronization issues will appear. If you are going to interrupt the threads, you should do it when you need it. This brings us to the preemptive multitasking, which is the basis of all modern schedulers.
We heard a word that perhaps not all viewers are familiar with. Help us out a little. What do we mean by preemptive?
The word preemptive means a kind of anticipation or reservation. It means that threads have priorities. More important tasks can preempt or interrupt the execution of a less important one.
To better understand preemptive multitasking, also known as real-time multitasking scheduling, we first need to know that it is designed for embedded systems. This means that we have a microcontroller in a relatively simple environment, and the CPU is expected to perform all tasks in a timely manner. In this context, it is not typical for a task to run indefinitely, as it might in systems like Windows. It is possible that a low-priority thread may run for a long time, but the important tasks must have enough time for the CPU. This is why we use the terms real-time and preemptive interchangeably. Real-time means that the system reacts to every event within a well-defined time. So not when the program arrives or when the corresponding time slice is running. Instead, what happens is that the event generates an interrupt or OS call, which wakes up the thread that is responsible for handling it. The preemptive scheduler is based on event-driven control. In an embedded OS, the basic idea is that the processor does everything important as soon as possible. But in the rest of the time, the microcontroller may have nothing important to do, in which case the idle routine is running, or the entire processor enters sleep mode. It may also occur that the threads that are doing the important things are waiting for the events they depend on. In this case, they are in a waiting state, called the suspended state. A thread can be taken out of the waiting state by an event. But what kinds of events can do this? An event can be, for example, an interrupt or a timer expiration, which is technically also an interrupt, or a call to an OS function. This can be, for example, calling a yield function. These events are always handled by the OS, including interrupts. With this information in mind, let's revisit our previous example using a real-time operating system.
Let's see our example using the RTOS, assuming that the OS is initialized properly. Our current example is almost identical to the very first example, when we didn't even use interrupts. There are two important differences. For opening the serial port, we added a comment indicating that this is an OS call. Ideally, the serial port handling is also provided by the OS. Let's assume that now. When the serial port is opened, the OS configures the hardware, enables the interrupt, and creates a FIFO to receive incoming data. It means that what goes in first comes out first. A FIFO is a container that allows data to be added and removed independently. It's also commonly referred to as a pipe. The serial port handler places data into one end of the pipe and the processor retrieves it from the other end. In an RTOS, the FIFO is also involved in event handling. When someone puts data into the FIFO, it also generates an event that wakes up the thread that is waiting for the data. The FIFO is, of course, part of the operating system, and every access to it is an OS call. The other difference is the reading of the data byte. In the first example, this was done by the program continuously checking the serial port control registers in a loop to see if any data was received. But here, what happens is the program simply takes the next byte out of the FIFO. But what happens if there's no data yet? This is the essence of RTOS. The task simply waits for the data. And while it waits, it goes to sleep, which means that its context is saved, its execution is paused, we could say that control is handed over, and the other tasks can run as needed. This works because reading from the FIFO is also an OS call. If the OS detects that there is no data, it automatically puts the thread into a sleep state. The thread remains suspended until something wakes it up.
What happens when a byte arrives at the serial port?
This generates an interrupt in the usual way. This time, however, our custom interrupt handler won't run. Instead, the OS's general interrupt handler will be executed. The interrupt handler checks what happened. In this case, data has arrived at the serial port. The interrupt handler takes the data out and puts it in the FIFO for the serial port. Here it is the FIFO operation that tells the OS that an event has occurred. When the interrupt handler has done its job, the control does not return to the interrupted tasks, but to the OS scheduler. It detects that data has arrived in the FIFO, so it changes the state of the waiting task from sleeping to ready to run. This does not mean that it will run immediately. Now the scheduler looks at which of the ready-to-run tasks has the highest priority and restores its context to memory. This is the one that will continue. Once the task has completed, our data waiting thread will wake up, retrieve the data, process it, and then wait for the next one. When all 100 bytes have been received, it calls the processing function. In the meantime, the incoming data accumulates in the FIFO. When it gets there again, it takes it all out, waits for the rest, and so on.
Thank you. I think you've shown this completely. What we could examine in more detail is what tasks and threads actually are and how they work. They are simple functions, mostly containing an infinite cycle in which they do their job. We can start these tasks by calling the appropriate OS function. There is also nothing to stop us from running the same function in multiple instances or calling the same function for multiple tasks, such as the data processing function in the previous case. In such cases, we say that the function is running in multiple instances. This is possible because when switching tasks, the operating system saves the context of each thread, allowing two instances of the same function to have separate contexts. But it's important that the context only applies to the function's own local variables, stored in a specific area of RAM called the stack, not to global and static variables.
Let's look at an example from a C program. In this example, I is a local variable of the processing function. It will be different in each instance. This is part of the context. It is saved when the thread is suspended. However, the sum variable is defined as static, so it is not stored on the stack. It is not part of the context. If the function runs in multiple instances, this variable will contain the same value in each instance. If one instance modifies it, the change will be visible in all of the others. This becomes problematic because the compiler doesn't know that this variable may be modified in the background. As a result, the generated machine code might not reload it from memory each time, but instead keep it in a register. The situation is different for the global _1 variable. You can see that the processing function doesn't modify its value, it just uses what's inside. Importantly, it is declared as a volatile int. This tells the compiler that the variable's value may change in the background at any time, so it must be reloaded from memory every time it is accessed, even if, in theory, that shouldn't be necessary. So in its current form, the processing function is not reentrant, meaning it will fail if it runs in multiple instances. If we remove the static tag from the static int sum equals 0 definition, the situation will be better. All internal variables will then become part of the context, and the global1 variable is intentionally global, so the function can safely be called in multiple instances.
It's good to know that the original standard library functions of the C language, such as printf, are not reentrant and cannot be run in multiple instances. This has been taken care of in newer implementations, but it's always worth verifying before using them in a multitasking environment. Now that we have a basic understanding of how the scheduler works, let's look at the other components of the OS. There are task management functions: create, delete, suspend, and query status. Among these, task creation is the most interesting. As mentioned earlier, a task is a function. In FreeRTOS, it must follow the form of void vtask code void star pv parameters. When this function is called as a task, some other parameters must be specified: the name of the task, its priority, a start parameter, and most importantly, the stack size. By understanding how the stack works, it becomes easier to see how the OS stores a task's context on the stack. All that happens is this: after the registers of the currently running task are pushed onto the stack, the OS redirects the stack pointer to a different memory location.
As shown here, the task1 and task2 threads each have their own separate stacks in memory. For example, when the OS interrupts task1 and transfers control to task2, the following steps happen. When task1 is interrupted, its stack pointer points to the top of task1's stack in memory. The OS saves this pointer value, and after completing its internal operations, it sets the stack pointer to the previously stored top of stack address for task2 and restores the register values from there, effectively performing a return from interrupt instruction. As we saw earlier, when starting a task, you need to specify the size of the stack. This will be the amount of memory that the OS will allocate to the stack of the task. If the size is too small, the stack may overflow, leading to difficult to detect program errors. Since the stacks of each task are stored consecutively in memory, as shown in the figure, if a task stack grows beyond its reserved size, it may overwrite the bottom of the next stack. This problem may only become apparent when the overwritten part of the other stack is accessed, often much later in the process. It is easier to avoid such an error than to find it, so it is worth giving plenty of stack space to the task if you have enough memory for the microcontroller.
As we have seen, in an RTOS, the execution of a task can be interrupted at any time by an external event. Then, the scheduler will run again, and if a higher priority task is woken up by the event, it will run until it finishes its task. For this reason, if two or more tasks share a common memory space, for example common global variables, you must be prepared for the possibility that the data stored there can be changed by another task at any time. Another common case is when multiple tasks need to access a hardware resource. Only one should be allowed to handle it at a time, otherwise the settings will be mixed up. This problem is similar to the interrupt example. Specific cases can be solved similarly, using flags that rely on atomic operations, but since this is a common and general problem, the operating system provides several built-in mechanisms.
One synchronization mechanism provided by the operating system is the mutex. Mutex stands for mutual exclusion. Technically, it is a token that can be held by only one task at a time. A separate mutex must be created for each shared resource. This mutex will protect that particular resource. For example, let's assume the shared resource is an ADC. The mutex is created through an OS call, which returns an identifier. This identifier is used by tasks that want to access the ADC. When a task wants to use the ADC, it must first request the token with an OS call. If another task has already acquired the mutex and hasn't released it yet, the requesting task will wait until it becomes available, ensuring that only one task uses the resource at a time. Therefore, once the task finishes using the ADC, it must release the mutex so that another task can use it. I should note that the use of mutexes can easily lead to 2 or more tasks becoming stuck. This situation is called a deadlock. In this case, both tasks are waiting for the other and neither can move on. This can happen when there are several shared resources between the tasks and they want to request additional mutexes. In the next chapter, we will cover this in more detail.
The next synchronization tool is the semaphore. Semaphore is often confused with mutex, but they are used for different purposes. A semaphore is used when one task needs to signal an event that another task is waiting for. This event can also be triggered by an interrupt routine. Accordingly, the use of semaphore has 2 basic functions: give and take. A semaphore typically contains a counter that increments when it is given and decrements when it is taken. If the counter of the semaphore is set to 0, and the task calls the take function at that time, the task will be put into a sleep state until another part of the program signals the semaphore.
David, I think we should hear an example for a better understanding.
Okay, let it be a simple example. You need to detect the button press with a task and run a simple function. A semaphore must be created for the button. The processing task calls the take function on this semaphore and waits for the event in sleep mode. Pressing the button generates an interrupt which triggers the corresponding interrupt handler. The interrupt handler signals the event using the give function of the button's semaphore, then terminates its execution. The event wakes up the button handler task through OS mechanisms, which runs the corresponding function, after which the task waits again for the next event, which will be the next button press.
I feel that we have succeeded in making the function of the semaphore clear. I would like to use this to introduce an improved version of the semaphore, called a FIFO. Here you can send not only a binary message to the receiving task, but also any data. The point is that data can be put into and taken out of the FIFO asynchronously, from independent tasks, and even from an interrupt, write-only in that case. The other important thing is that the receiving task can automatically wait for the data to arrive and remain suspended until the data arrives. In practice, data reads usually include a time limit, called a timeout. If no data arrives in the FIFO within that period, the thread wakes up and the read function returns with a timeout error instead of a valid data. This allows it to handle situations where data transmission is interrupted, ensuring that the receiving task doesn't remain suspended indefinitely. The elements of a FIFO are not necessarily bytes. They can be complex data types or pointers to them. Queues and message buffers are similar mechanisms with slightly different implementations and properties depending on the OS, but we won't go into detail here.
We also have to mention timers, although they are not specifically for synchronization between tasks, but managing timers is an important part of the OS features. There are basically 2 types of cases. One is when the task has nothing to do, but wants to wake up in X amount of time to do something. In this case, it makes a timed sleep call to the OS, which puts the task to sleep and wakes it up after X time. Similarly, so-called blocking instructions, such as waiting for a semaphore, can include a maximum time limit called a timeout. After this timeout expires, the thread wakes up even if the expected event has not occurred. The other case is slightly different from the previous one. In this case, a timer is created at the OS level, similarly to how tasks are defined, and a callback function is assigned to it. The timer will call this function at a specified time or at regular intervals. This is a bit similar to creating tasks, but this callback function must execute and return quickly. In this, it is similar to interrupt handler. This type of timing can be used to allow the processor to perform a specific task at a given time or frequency, or to generate events for other tasks.
Finally, let's say a few words about memory management. The 2 ways of storing variables have already been touched upon. Global and static variables are stored in predefined areas of memory, while local variables are stored on the task's stack. There is also a third memory type called heap. The heap is not the same as the stack. It refers to the remaining memory in the system that is not pre-allocated. Of course, it is possible to use this memory space with dynamic memory management during runtime. In this case, we decide when and how much memory to allocate or release. However, it is important to keep in mind that we have to take care of freeing the allocated memory. In C, we can use the malloc function to allocate available memory space. Then the free function is used to release the reserved memory areas. In embedded systems, it is advised to avoid dynamic memory management, but usually it is not even needed. However, if it cannot be avoided, it is important to remember that using shared memory is inherently unsafe. Therefore, such operations must be performed through the operating system, and standard C language functions cannot be used. Different OSs provide a wide variety of solutions for memory management, depending on the complexity. In FreeRTOS, for example, we can choose from 5 different memory allocation schemes, depending on how we intend to use the allocated memory.
This marks the end of our introduction to the RTOS and its basic features. It is good to know that especially for FreeRTOS and similar simple OSs, a mixed programming style can be used. This could mean, for example, that while you have a scheduler and tasks, some operations are still handled by traditional interrupt routines that do not interact with the OS, but run under it without the OS knowing about it. For example, in a low priority task, we monitor an event in a silly way by continuously polling for it, that is, repeatedly checking its status instead of using a proper OS service. This often makes the program simpler or faster, but of course also uglier from a programmer's point of view. One of the advantages of FreeRTOS, as mentioned earlier, is that it is available at the source code level. So we can follow exactly what happens and even hack it if needed. You can even rewrite it, but that's really a pastime for the very determined. Arriving at the end of today's chapter, let's summarize when and why it makes sense to use an OS.
When developing a large and complex program, it makes sense to always use the same tools for each type of task. This makes the program easier to understand and makes it easier for several programmers to work together. RTOS is such a collection of tools for performing independent tasks that appear to run in parallel on the processor. Thinking in terms of operating system allows us to break down complex tasks into simpler subtasks more easily.
Along with the operating system, we get a lot of other services that we don't have to write anymore, not to mention that the OS can be easily supplemented with additional functions such as network management and file management. These are complex tasks in themselves, and although they can be used without an OS, integrating them into the OS allows any task to access them.
Multi-threaded programs are very difficult to debug. This is also true for OSs. However, in many cases, a suitable add-on is available for debuggers. This is OS aware. These tools make it possible, for example, to pause one thread while others continue running, or even to debug the entire system and inspect the state of all tasks.
Of course, there are downsides of using the operating system. Perhaps the most important is the need for the right knowledge and experience, since even a simple OS is complicated enough. For the software to function properly, all team members need to have sufficient experience.
When using the OS, it's easy to make hard-to-spot mistakes, which sometimes have a rare unintended effect.
The OS has some plus memory requirements and so-called overhead. The memory requirements can be more significant due to the separate stack requirements of the tasks, although the other parts, such as FIFOs, mutexes, timers, all use memory. Overhead refers to the extra processing time and CPU usage required to run the OS, for example, to switch between tasks and manage inter-task communication.
Program execution is not deterministic. It can be interrupted at any point and resumed on a different thread. This makes it difficult to follow its operation, even if the debugger is OS aware. When using the OS, debuggability is only an advantage when implementing a complex program, otherwise the OS tends to complicate debugging. In general, a program with linear architecture is much easier to debug and understand than any OS-based application.
Finally, let's look at some common mistakes that are easy to make when reusing an OS. Lack of re-entrance and improper use of global variables. All tasks functions and functions called by tasks must be re-entrant. If you need to call a function that does not fulfill it, you should synchronize its call, for example by using mutex.
Using an infinite loop to wait is a common technique in traditional programming, but in an OS environment it prevents lower priority tasks from running and should therefore be avoided.
Stack overuse? If this happens, it can be very difficult to identify the source of the problem. Some operating systems include protection mechanisms against it, but these come at the cost of additional overhead.
Competing data access occurs when multiple tasks simultaneously read from or write to the same memory. This can cause unpredictable errors, but it can be avoided with proper synchronization.
Failure to release a resource, such as mutex. For example, a function may acquire a mutex, but then exit via an error branch without releasing it. As a result, the mutex remains locked, and other tasks are unable to access the resource.
Deadlock, which is a condition where two or more threads wait for each other to release a shared resource. This can occur, for example, if task A reserves mutex X and then waits for mutex Y. Meanwhile, task B has already reserved mutex Y, but still needs mutex X, which A has already reserved in the meantime. They will never get out of this situation. One way to avoid this is to ensure that a task does not hold more than one mutex at the same time, or by using a timeout when waiting for the second mutex. If it fails to get the resource for a certain amount of time, it will also release the previously busy mutex and then try again later. The point is that the programmer should be aware that this situation can occur.
This brings us to the end of the chapter. Now you are aware of the basic function of the RTOS. It's worth trying out in practice.
Thank you for joining us in this theoretical chapter. You can find and download the written materials for Crystal Clear Electronics on our website, crystalclearelectronics2.eu. Follow us on Facebook to be the first who gets notified about the upcoming videos and other news. See you soon in the next video. Until then, have a great day.
Bye.